Welcome back to Space Repo, your portal to the cosmos. Have you ever dreamed of zipping across the galaxy, visiting distant stars, and returning home with tales of your adventures? It's a classic sci-fi fantasy, but what if I told you that the very laws of physics make this dream a heart-wrenching paradox? The faster you go, the more you leave behind, not just in space, but in time itself. This isn't science fiction, it's one of the most mind-bending consequences of Albert Einstein's theory of relativity. It's a phenomenon called time dilation, and it's the universe's ultimate speed limit, ensuring that a trip to the stars might mean you can never truly come home again. Einstein's special theory of relativity, published in 1905, turned our classical understanding of space and time on its head. Before Einstein, we thought of time as a universal constant, a steady, relentless river flowing at the same rate for everyone, everywhere. But Einstein showed us that time is not absolute. Instead, time is relative. Its passage depends on your motion. Specifically, the faster you move through space, the slower you move through time relative to a stationary observer. This might sound bizarre, but it's a proven physical fact, measured countless times in laboratories with atomic clocks and even observed in GPS satellites orbiting the Earth. Think of it like this: space and time are interwoven into a single fabric called spacetime. Everything in the universe is constantly traveling through this spacetime. If you're standing still, you're traveling primarily through the time dimension. But as you start to move through space, some of your travel is diverted from the time dimension into the space dimension. The total speed through spacetime is constant for everything, the speed of light. So, the more you allocate your speed to moving through space, the less speed is left for moving through time. For everyday speeds like walking or driving, this effect is so minuscule it's completely unnoticeable. But as you approach the speed of light, the effect becomes dramatic. Time for the traveler would slow down to a crawl compared to time back on Earth. This brings us to one of the most famous thought experiments in physics, the twin paradox. Imagine two identical twins, let's call them Stella and Tara. Stella is an astronaut who embarks on a journey to a star system 10 light-years away. Her spaceship is incredibly advanced, capable of traveling at 99% the speed of light. Tara remains on Earth, waiting for her sister's return. From Stella's perspective inside the spaceship, the journey feels relatively short. Because she is moving so fast, time for her slows down dramatically. The 10 light-year distance also contracts from her point of view, another consequence of relativity. For her, the trip to the star and back might only take a few years. Let's say for Stella, the round trip takes a total of 5 years. She lands back on Earth, excited to reunite with her twin, expecting Tara to be just 5 years older. But when she steps out of her spacecraft, she is met with a shocking reality. On Earth, time has passed normally. While Stella was experiencing 5 years, decades have passed for Tara. Her twin sister is now an old woman, or perhaps long gone. Everyone Stella knew has aged significantly, and the world she left behind is irrevocably changed. She has effectively traveled into the future. This isn't a paradox in the sense of a logical contradiction, it's a proven consequence of how our universe works. The paradox comes from the question of why Stella is the one who aged less. From Stella's perspective, wasn't Earth moving away from her at 99% the speed of light? Shouldn't Tara be the younger one? The resolution lies in the fact that their situations are not symmetrical. Stella had to accelerate to near light speed, turn around at her destination, and then decelerate to land back on Earth. Tara, on the other hand, remained in a single, relatively non-accelerated frame of reference. It is the acceleration that breaks the symmetry and makes Stella the one who experiences less time. So, interstellar travel at near-light speed isn't just a journey through space, it's a one-way ticket to the future. You could travel to the Andromeda Galaxy and back, but upon your return, millions of years would have passed on Earth. Humanity itself might not even exist anymore. This time dilation effect is a fundamental barrier to the kind of interstellar civilization we see in movies. But there's an even more fundamental roadblock that prevents us from ever reaching the speed of light itself: energy. Einstein's famous equation, E=mc², tells us that mass and energy are two sides of the same coin. As an object with mass accelerates, its kinetic energy increases. But according to relativity, this added energy also increases its relativistic mass. In other words, the faster you go, the heavier you get. This isn't just an abstract concept, it's a tangible resistance to further acceleration. As you push an object closer and closer to the speed of light, its mass approaches infinity. To accelerate an infinite mass, you would need an infinite amount of energy. Since there isn't an infinite amount of energy in the universe, it's physically impossible for any object with mass to ever reach the speed of light. Only massless particles, like photons of light, can travel at this ultimate cosmic speed limit. They don't experience time at all. From a photon's perspective, its journey from a distant star to your eye is instantaneous, even if it took millions of years from our point of view. So, if we can't reach light speed, what does that mean for exploring the galaxy? It means that even our nearest stellar neighbors are incredibly far away. Proxima Centauri, the closest star to our Sun, is about 4.2 light-years away. Even with a hypothetical spacecraft that could travel at 10% the speed of light, a one-way trip would take 42 years. A round trip would take over 84 years, not even accounting for the time needed to accelerate and decelerate. The crew that arrives would be a generation or two removed from the crew that left. This is the concept of a generation ship, a self-contained world journeying for centuries through the void. The vast distances and the unyielding laws of relativity paint a picture of a lonely universe. We may be confined to our own cosmic neighborhood for the foreseeable future. The stars we see in the night sky are like tantalizing islands across an impassable ocean of space-time. While we may never break the light-speed barrier, understanding these principles is crucial. It shapes our search for extraterrestrial life, reminding us that a signal from a distant civilization could be ancient history by the time it reaches us. It also pushes us to think of more creative, albeit theoretical, solutions. Concepts like wormholes or warp drives, which propose to bend or fold spacetime itself rather than travel through it, are ways of trying to circumvent this cosmic speed limit. While purely speculative for now, they show humanity's relentless drive to explore and to one day, perhaps, bridge the impossible distances between the stars. The universe is a vast and mysterious place, governed by rules that are both elegant and unforgiving. Time dilation is a perfect example of this. It's a key that unlocks a deeper understanding of reality, but it also locks the door to our simplest dreams of galactic exploration. The journey to the stars is not just a challenge of engineering, but a confrontation with the fundamental nature of time itself. Thank you for joining us on this journey through space-time. If you enjoyed this exploration and want to unravel more mysteries of the cosmos, be sure to subscribe to Space Repo. Until next time, keep looking up.